pleasure to have Wesley Fussner here visiting us from the Institute of Computer Science, Czech Academy of Science. And he's going to tell us about interpolation and substructural logics.
Thanks, Peter, for the introduction. Thanks, everyone, for being here. So, yeah, I want to talk a little bit about recent progress on the study of interpolation. I would argue generally, but particularly using substructural logics as a platform, a lens through which to understand general notion. So let me dive in and talk a little bit about what I mean here. So what is interpolation, generally speaking? So interpolation is actually a cluster of different ideas, a cluster of different metalogical properties. The core of it is that if you have some formulas, perhaps, or some logical structures, A and B, and you have that A entails B, then there exists some other thing, I say, and I deals only with the subject matter common to both A and B. And you have for this I, A entails I, and I entails B. And there are a lot of undefined primitives here that I've kind of alluded to. I is usually called an interpolant, first of all, and it gives some kind of an explanation for why A entails B. That's kind of the general idea of what interpolation is about. But there are these intuitive notions, entailment, common subject matter, and I haven't defined this. There are many different ways of caching them out, which are inequivalent and have particular native environments that might be useful in particular contexts. Here are some variants. Probably the one most people understand is Craig interpolation. Craig interpolation says that if you have A implies B in some logic, this is a provable theorem of some logic, then there exists some formula whose variables are common to A and B, so that A implies I and I implies B. Now, Craig interpolation is very much fixed for a particular language. You might want to deal with certain kinds of logical contexts where there's more than one conditional, or where there are other connectives that behave in a conditional-like way. Because of this, you might want to free the language of this dependency on individual connective, which is where deductive interpolation becomes useful. Deductive interpolation merely swaps out the implication connective by some consequence relation and rehashes interpolation in a deductive environment. I could go on listing different variants of interpolation all day because there are many, many of them. One that's perhaps quite prominent in computer science these days is uniform interpolation. The technical version of it's right there. Perhaps it's easier to understand the idea of uniform interpolation than just to understand the technical aspects. Uniform interpolation basically just says that you may select the interpolant uniformly once you're given one of the sides.
This last formulation, you mean 45 over 8 for any A?
Yeah, for any A. Any A. This is a left-hand version. You could have a right-hand version as well. You could have many versions of this. This is a left-hand version of uniform interpolation. You might have a right-hand version. There are many other kinds of different interpolations, Linden interpolation and so forth. And I won't go into these.
So you're mostly talking about propositional logic here or first order logics? What are the variables?
This is all phrased for propositional logics. If I deal with first order logics, I have to get into some predicates and stuff like that. Some of the things I say will also apply to first order logics, but I would like to keep things as simple as possible. Now, some applications of interpolation. People care about interpolation for many different reasons. Probably the first and foremost are philosophical issues or purely logical issues. Interpolation has a purely logical meaning, which I think is appealing to many of us. Those more practically minded may know about the applications to hardware and software verification. This is in particular the Ken McMillan approach of doing these kinds of things. It's very prominent. It's very useful in automated verification. Uniform interpolation we use a lot in database theory. Sometimes we're using some of this stuff for SMT solving these days. There are new and exciting directions all the time. Now, kind of the linchpin of this talk, you might think about going back to the early work on this, a lot of which was done in the 70s leading up through, and then culminating in this famous monograph of Doug Galai and Marissa Maximova. And in the foreword to their monograph, they have this kind of pregnant quote. Interpolation turned out to be a treacherous subject. There are many published proofs by well-known researchers that were later found to be wrong, leaving the result open with neither proofs nor counterexamples. Although in general, we have some idea of how and why interpolation may hold or fail for a given system, we still have the persistent feeling that really we need to obtain our results, if we can, logic by logic, case by case, and that a slight variation in the logic may change the outcome. Yet we feel that interpolation is a coherent research area, and we just have to wait and see to figure out what is going on. So one thing that I would like to convince you of today is that at least in the context of substructural logics, we are really on the precipice of understanding what is going on. We have something starting to approach a coherent picture. This talk is based on the following papers, which are all in the last few years. I think this stuff has changed a lot in the last 5 or 10 years. Many of these have already appeared. Some of them are still under review. A couple of them I have not yet put on the archive yet because I've been too busy talking to some of you guys. Watch for them, they'll be there. This stuff is all available if you want to learn. So I want to start in general terms. I won't mention substructural logics at all in this first part, but I'll try to give you some idea of the tools of the trade. How do we study interpolation in general terms for whatever logic you may be interested in? Probably the start of any conversation about interpolation, at least for substructural logics, should come down to proof theoretic techniques. There are famous techniques going back to Mahara's work that take some calculus, analytic sequent calculus, for example, and start with an implication that's provable, and syntactically using some kind of partitioning methods, they algorithmically extract Craig interpolation. This works in some kind of nice circumstances where, first of all, there is available such an analytic proof theory and analytic calculus, some adequate proof theoretic formalism. But for the same reason, it's sharply limited by this, okay? Because I think it's sort of consensus among logicians today that relatively few logics have good proof theory in this sense. In fact, one reason that you can argue for this, one reason that you could argue that few logics have a good proof theory is some recent work of Rahul GALAI and Amir Tabatai, where they actually take some general proof theoretic environment, and they show that in this general proof theoretic environment, if you have such a good analytic calculus, then you do have Craig interpolation. And so in some sense, if you have nice enough proof theory, it's totally inadequate for studying interpolation because you can't get at the cases where it fails. You can't get at the cases where perhaps you have deductive interpolation, not Craig interpolation. And so it's not very poignant for understanding general questions, big picture questions. And that's mostly what I'm after. Another approach, which I think is in line with the interests of a lot of people here, is to approach things algebraically. So if I take some kind of deductive system, some kind of consequence relation, and I think about it having a good algebraic semantics, which is quite a common feature of many logics, then under appropriate technical circumstances, the consequence relation enjoys the deductive interpolation property precisely when its algebraic semantics enjoys the amalgamation property. Amalgamation property is a commonsensical logical algebraic property that has been studied quite extensively. And if you might think about interpolation from this vantage, and you're at least interested in deductive interpolation, and often Craig interpolation on the periphery, then the major question becomes, how do you study the amalgamation property? How do you establish or refute the amalgamation property? And in big picture terms, the answer is to reduce the complexity of the problem to some tractable generating classes with algebras. And I'll talk a little bit about how to do that. Here's a technical definition of amalgamation if you don't know what it is. I think perhaps reading the technical definition is not that useful, but what this says in broad terms is if I have a span of algebras in some class, that's the left-hand side of the diagram here. I have some algebra A, and it embeds in some algebras B and C. The amalgamation property says that I can complete this commuting diagram by finding some D in there and some embeddings of B and C in there. And this diagram should do. That's what amalgamation is. Strong amalgamation says that I can do this, and moreover, when I chase A through the diagram, it turns out that the intersection of B and C in this amalgam is exactly A. I get nothing more in the intersection. The idea of amalgamation comes from the study of groups. And so I think you can think about this quite intuitively by thinking about group theory. Here are some common sensical groups that we know. Yeah.
Is the strong amalgamation property exactly asking that the diagram is a push-out, or is it strong?
There's no universality. So there could be many strong amalgams. Yeah, so these are groups that we all know. We have Z3 and we have the Klein 4 group. And here I've denoted their intersection in a particular way. I've named the elements so they precisely intersect with the trivial group. The natural question that you could give to a first-year algebra student or something is to just slam these groups into one common multiplication table and ask if you could complete this into. This could be completed into a group precisely if this 6-element thing is a strong amalgam of the two groups. And if you play around doing some calculations, you could find in less than 5 minutes, I would say, that you can't do this. There is no amalgam on 6 elements. On the other hand, there is an amalgam of these two groups in the category of all groups, say. I could take, for example, their direct product. And something this implicates is the fact that I don't know how big the amalgam should be. I might take amalgams and I might have to grow this multiplication table with arbitrary bound, right? And so this implicates some kind of algorithmic questions. How can I actually decide whether I can amalgamate two things? Well, there are some limitations, thankfully. In principle, I might not even need an infinite amalgam, right? In principle, I might take small finite groups, and maybe there's no finite amalgam that there is an infinite one. At least I can bound cardinality. At least the amalgam can be taken to be countable because of the following theorem. This has kind of a tidy proof that uses first-order model theory. But what the theorem says that if I take any universal class of algebraic structures, and I suppose that every span of finitely generated algebras has an amalgam, then the whole class has an amalgamation property. And why is this true? So I think it's interesting to go through the proof of this because the proof maybe isn't obvious, but it's very tight, it's short. So if I take a span in this class, I can assume without loss in generality that A is actually a subalgebra of B and C. So the maps, the embeddings are actually inclusion maps. Then I could take, say, sigma to be the union of the theory of K with the atomic diagrams of B and C. In other words, because B and C are finitely generated things, I can write down some finite presentation of them, and I can write down some finite diagrams for this, right? Now then the amalgam, the span has an amalgam if and only if this sigma has a model. And I can reduce this by compactness to thinking about finite subsets, right? So I could consider sigma prime to be the theory of K with any finite subset of the atomic diagram. And I can just take the corresponding subalgebras, and I get, by assumption, that this has an amalgam in K. So by the compactness theorem of first-order logic, the result follows immediately. So at least we can limit our search if we're looking for amalgams to countable algebras. And this is something nice to know. This kind of theme of looking for more tractable ways of finding the amalgam will show up repeatedly in this talk. Now, I can't really continue to talk about any of the technicalities without hitting on some topics from universal algebra, because it gets to be rather technical to phrase some of these things. I think everybody here knows some universal algebra, maybe not at this level of generality. Most people probably think about varieties, equational classes. And a lot of this stuff should properly be phrased in terms of quasi-varieties. Quasi-varieties are somehow where you have a bunch of equations that implies another equation. And in this context, there are a lot of the usual universal algebraic machinery like congruences, subdirectly reducible algebras, and so forth. They must be relativized. So I have to take note of the fact that quasi-varieties are not closed under homomorphic images, and only consider things where I do have closure on this, right? And these are just some standard definitions. Whenever I say Q congruence extension property, Q subdirectly irreducible, I'm just referring to the relativized notion to a particular quasi-variety. The definitions are here. Maybe it's not worth going through. Is it worth talking through this? Or?
Maybe you could retrace that.
All right. So I said what a quasi-variety is, right? The second point is that if Q is a quasi-variety and I take some algebra in the quasi-variety, then a congruence of that algebra is a Q congruence. If when I mod out by it, I'm still in the quasi-variety. It need not be true in general. I will say that an algebra is finitely Q subdirectly irreducible if the least congruence is media reducible in the lattice of all Q congruences. If it's completely media reducible in the lattice of Q congruences, then I'll just say that it's Q subdirectly irreducible without the finitely. I'll drop all of this stuff when Q is clear from context, and I'll refer to the class QRFSI and stuff like that for the class of finitely subdirectly irreducibles of Q. I'll say that Q is Q congruence distributive if the lattice of Q congruences of the algebra is a distributive lattice. And I'll say that Q has the Q congruence extension property if whenever I have an algebra in Q and A is subalgebra of that algebra B, and theta is a Q congruence of the little algebra, then there exists a big algebra psi, congruence on the big algebra, so that theta is exactly psi intersection with A, restriction of psi. So I can take congruences on the small algebra and they can always be blown up to the super algebra. This makes sense. Now, a lot of the progress that's been made in studying deductive interpolation comes from studying amalgamation. And a lot of the progress we've made studying amalgamation comes from transfer theorems. As I said, we somehow reduce the complexity of studying amalgamation to some kind of nice tractable generating classes for algebras. Here's an example of such a transfer theorem. It's a slight generalization of some earlier ones due to George Metcalfe and Kostas Sinakis and some other people. And it says, if I take a subclass of a quasi-variety Q, and I assume four things of this, then Q will have the amalgamation property. What must this subclass satisfy? So first, this subclass K must be closed under isomorphisms in subalgebras. Second, every relatively subdirectly irreducible member of the quasi-variety has to belong to the subclass. The third item is something like a weak version of this congruence extension property, or Q congruence extension property. But for intuitive purposes, you can just understand it as congruence extension. And the fourth is that every span, I say doubly injective for this is redundant, but every span of finitely generated algebras in K subclasses must have an amalgam quasi-variety. If these stipulations are met for any class K, then I have that Q has the amalgamation property. So this is a decent, sufficient condition. It's been applied quite a lot in the literature, and things like it have been applied quite a lot in the literature to show that such and such quasi-variety does have.
What do you mean by double injective?
I just mean span. In the literature, you might see doubly injective for referring to the fact that I really have two embeddings coming out of A. That need not be.
They need to be embedded.
They need to be embeddings.
By the way, what is relatively subdirectly reducible?
So A is relatively subdirectly irreducible. This means that it's Q subdirectly irreducible relative to Q. So in other words, if I look at the lattice of Q congruences of the algebra, then the least Q congruence is completely media reducible. Whenever I write it as an intersection of any Q congruences, it has to belong to this.
The reference of the theorem is mistaken, right?
No. So there's an early version of this that you might think due to Kostas.
Okay, oh yeah.
But this is an improvement because it deals with quasi-varieties and it deals with finitely generated spans.
Finally generated. I see now. Okay, yes. I see.
Yeah, so there's an antecedent of this which is very well known, which has been applied a lot from 2014.
Yeah. I see. Oh, very good.
Now, you can do even better. What I gave you are some sufficient conditions, okay? What I would really like is not just sufficient conditions that tell me that I can establish the amalgamation property, because I think there are many techniques for establishing that something has the amalgamation property, perhaps directly. What I would really like if I want to study something systematic is I want good criteria that tells me the amalgamation property fails. And I think it's already clear kind of from these examples of finite groups that this is a tall order. If for some reason these groups that I gave you could not be amalgamated in any groups, I think it would be rather hard to show that because the possible amalgam grows without bound. Perhaps I have to consider all countable groups. It would be really a chore to show this, right? So what I would like is some necessary and sufficient conditions. One comes from considering the so-called one-sided amalgamation property. The one-sided amalgamation property is really the same as the amalgamation property, except when I complete this diagram, when I complete the D, I drop the requirement that both of the maps going into D are embeddings. Instead, one can just be a homomorphism. If I can always do this so that I get such a completion of the commuting diagram, that's the one-sided amalgamation. Now, this turns out to give a complete characterization of the amalgamation property under some technical hypotheses. So in particular, if I take Q to be any quasi-variety with the Q congruence extension property, and I assume the class of relatively subdirectly irreducibles, finitely subdirectly irreducibles of the quasi-variety are closed under subalgebras, very closely related to something called equationally definable principal means. It's something like having a disjunction in the corresponding logic. So it's quite commonsensical for logical purposes. If I have those hypotheses on the quasi-variety Q, then the following 5 things are equivalent. First, the quasi-variety has the amalgamation property. Second, quasi-variety has the one-sided amalgamation property. Third, if I just restrict to the relatively finitely subdirectly irreducibles, then that has to have the amalgamation property too. And now this is a much smaller class. This is a class for which I can actually work with things and test things, hopefully, if I could get a good tangible handle on the relatively finitely subdirectly irreducibles.
And you asked for the amalgam to be in the class, right?
In that class,
In
right?
that class.
So for example, for many applications that people have thought about, the relatively subdirectly irreducible algebras turn out to be totally ordered or something like that. And if you're in that kind of situation, you don't just try to amalgamate things in any kind of algebras. Then you know the amalgam has to be a totally ordered algebra. This is really a tractable thing to work with. There are many such similar applications. And there are a couple of other equivalents here which are more of technical interest, right? You can bound some things on the size of some direct products and so forth.
Was this known for varieties, or is it, if Q is a variety, is this result also new?
Yeah.
Oh.
For Q of variety, this is also new. And I should say, a lot of these things are of primary interest for varieties. If I'm more dealing with varieties of algebras instead, I should just drop all of the relative. Where it says relative, it just becomes the usual variety. But yes, this is new for varieties as well. Now, a happy consequence of this, going back to this kind of search for amalgam question, is that this implies some decidability results. So let me tell you that a variety is finitely generated. I'm now specializing to the variety case. This is, I think, not true for quasi-varieties in general, but it is true for varieties. I'll say that a variety is finitely generated if it is generated as a variety by some given finite set of finite algebras of finite signature, everything finite. So finite signature is probably quite commonsensical, but I just assume that it's generated as a variety by some finite set of finite algebras, or equivalently a single finite algebra. Under that hypothesis, let's suppose that I take a variety and it's finitely generated in congruence distributive, and I assume that its class of finitely subdirectly irreducibles is closed under subalgebras. Then there's an effective algorithm to decide if the variety has the congruence extension property and also the amalgamation property. You could implement this if you want. The algorithm is quite transparent. I think the complexity is quite bad. Complexity is necessarily bad because for an appropriate choice of variety, this is equivalent to some P versus NP stuff. So some difficult complexity theoretic questions.
Yeah, wait.
But you could implement it, and probably if you're interested in some small algebras, you could actually solve many problems using the algorithm is outlined in the paper. There are many other techniques. There are many other kind of tools that you might use to study amalgamation in different contexts. In particular, ones coming from injective objects, having enough injectives in different classes and categories. But one thing that I will mention, some particular use for some applications in substructural logic comes from so-called essential extensions.
Sorry, go back to the algorithm. The algorithm returns yes or no.
Yes.
It is not that if it is, then it returns yes. If it is no, it gets.
It'll return yes or no.
It will return yes.
And the algorithm actually first tests whether the variety has the congruence extension property. You can just do it on the finitely subdirectly irreducibles. And there are some results, some old results, essentially from Keith Kearns and people like this that tell you that for residually finite varieties, if you have the amalgamation property, then you do have the congruence extension property, right? So if that first step succeeds and you do have the congruence extension property, then you can check whether it has amalgamation. So it's a two-stage algorithm in a sense. Now, essential extensions. I'm very excited about this particular presentation of what amalgamation means because it's been really key to solving some old problems for us. So if I take A and B to be algebras, I will say that a homomorphism, say phi from A to B, is an essential embedding if every congruence of B, for every congruence of B, as long as that congruence is not the diagonal, it's not the least congruence, then its intersection with the image of A can't be the diagonal in the image. Makes sense? The idea here, maybe the embedding actually conceals what's going on, but you might just think about A as being a subalgebra of B. And the idea is that containment, that inclusion is an essential containment. If whenever I take a congruence on the big algebra, that's not just the trivial congruence, I restrict down and I still don't have the trivial congruence. That's what it means to be essentially embedded. Now I'll say that a span, which I've written as a pair of morphisms here, I'll say that a span is essential if just one of the maps is essential embedding. And I'll say that a class has the essential amalgamation property if every essential span in the class has an amalgam. The theorem about this is as follows. If I take a variety with the congruence extension property, and I assume that the class of finitely subdirectly irreducibles is closed under homomorphic images and subalgebras, then the variety has the AP if and only if the finitely subdirectly irreducibles has the essential AP. The purpose of this and the use of this is essentially for varieties that are generated by totally ordered algebras. Because if I consider a totally ordered algebra, at least of the type that typically shows up in logic, maybe this is some kind of logical unit, then actually congruences are determined by some kind of filter, some kind of thing around one, right? Some upset here. And it's very easy to see, first of all, if these are closed under homomorphic images and subalgebras usually. And it's very easy to get a handle on essential embeddings in such contexts, right? Because I should know exactly how filters like this are served. This has been key for some of the applications that I'll show. So this is kind of an overview, perhaps overly technical overview, but these are the key tools that have allowed for a lot of progress in the last few years. Maybe I'll ask, are there any questions before I move on to the next part?
Essential means that to identify something in B, you have to identify something in A.
Exactly.
Kind of means that B is not big. You're shrinking B until it's can collapse any. There's no stuff in B that's independent of having A.
It's like A is everywhere.
Yeah, there's some connection between A and B, which is essential to this.
That's why you chose the word essential.
No, it's well known.
It's a
Categorical thing.
category.
So I haven't mentioned substructural logic up until this point, let's talk about substructural logic. So I'll now try to use some of the things that I have just discussed to talk about the state of the art of interpolation in substructural logics. So maybe some historical points. Interpolation, I think everyone knows, goes back to Craig, who was working on interpolation for classical logic in the 50s. Perhaps from the substructural point of view, this kind of started to take off in Maximova's work in the 1970s about superintuitionistic logics, extensions of intuitionistic logic. She showed, among other things, that there are exactly 8 superintuitionistic logics that have Craig interpolation. It's equivalent to deductive interpolation in that context. Later on, GALAI and Pitts and other people discussed uniform interpolation and superintuitionistic logics. A lot of the work on substructural logics goes back to the relevant logicians and what they were doing maybe in the 80s, 90s. And in 93, Urquhart showed that both the deductive interpolation theorem and the Craig interpolation theorem fail for relevance logics, most of them. Although there are some special ones in the vicinity of the Mingle rule for which this works. There was also some classifications of the deductive interpolation property for Lukasiewicz logic, kind of a commonsensical fuzzy logic. This is completely classified since 2000. Craig interpolation is also completely known there. Essentially, none of them have Craig interpolation. Deductive interpolation, there are infinitely many. And in the early 2000s, Franco Montagna showed that there are uncountably many extensions of Hayek's basic fuzzy logic that don't have deductive interpolation. The problem, positive question, which ones do have deductive interpolation, was only solved this year. And I'll talk about the solution to this. So a little bit, probably for most people in this room, I can skip this slide, but a residuated lattice is defined like so. These things are the algebraic semantics of substructural logics in much the same way that Boolean algebras are the algebraic semantics of classical logic. In brief, a residuated lattice is some algebraic structure that is composed of a lattice, first of all. Second of all, it's composed of a monoid. And the monoid and lattice structures are linked by this kind of residuation law that's in display there. Namely, whenever I have x times y is smaller than z, smaller is in the lattice order here. That means that y is smaller than some x under z, and it's the same as saying that x is smaller than z over y. I should think of these divisions over and under as being two implications, where x under z is like x implies z going in one direction, and z over y is like z is implied by y going in the other direction. So we'll use all the expected algebraic terminology in the setting. When I say something is commutative or idempotent, I'm referring to the monoid part, right? Commutative, idempotent monoids. Totally ordered means the lattice order is totally ordered, etc. One particular thing that's useful, some terminology that I'll use often, I'll talk about semilinearity. Semilinearity means that an algebra is a subalgebra of a direct product of totally ordered residual lattices. So it's in the variety generated by linearly. And for many logical contexts, we also want an additional operation. We want an additional additional Norlier operation that gives me like a falsity constant. And in that case, I'll denote it by F. In that context, they're usually called FL algebras or pointed residual lattices. Now, maybe the start of the story, because these things come from the algebraic semantics for substructural logics, the start of the story comes from basic structural rules from proof theory. These are all structural rules that you can find in Genson's original work on presenting sequence-style presentations of intuitionistic logic. The common structural rules, the most basic ones from top to bottom, left to right here, are the exchange rule, which kind of says that hypotheses in a deduction can be commuted. The contraction rule says that I can squish down, going from top to bottom on the sequence calculus, I can squish down hypotheses, contract. I is something called left weakening. This says that I can produce new hypotheses in the left in the sequence. Right weakening is displayed in this O. right here, which is some other kind of weakening thing. Mingle is a less powerful version. It looks rather complicated here, but it's a less powerful version of these weakening rules. It's easier to understand what this mingle rule says if you think about it algebraically. If I think in terms of algebraic semantics for residuated lattices, the exchange rule just says that this multiplication is commutative. The contraction rule just says that the multiplication is square increasing. And the mingle rule just says that the multiplication is square decreasing. All of these things are satisfied in intuitionistic logic, for example.
What do you need? I remember mingle used in cut elimination.
Uh,
Do you remember the connection between mingle and cut elimination?
Many calculi with mingle do have cut elimination. But of course, you might have lots of contexts in which you have calculi with mingle that are not analytic. Now, one point about interpolation in the basic substructural logics, ones defined by these basic structural rules, is that the exchange rule has an extremely critical role. A little bit of history about this. There's been lots of success in finding logics with exchange that have the deductive interpolation property. For example, all of Maximova's success is in this context because exchange is satisfied in intuitionistic logics. On the other hand, without exchange, we've had much worse luck. It was previously thought that there may be no extensions of the full lambic calculus, the basic substructural logic, that lack exchange but have the deductive interpolation property. I think that was a conjecture of Jose quite some time ago, right? Yeah. And finally, some people in this room gave an example of a substructural logic that lacks the exchange rule. So the exchange rule is not derivable, but it does have the deductive interpolation property. That was just in 2020. And since then, there have been several natural examples that Nick Vlados and I have given, kind of related to the law of excluded null. So it's known now that there can be some logics without the exchange rule that nevertheless have nice interpolation properties. I would like to kind of paint a bit of a picture about the role of exchange among substructural logics generally. And maybe the first thing in this picture comes from this theorem. If I take varieties of commutative residuated lattices, pointed commutative residuated lattices, then among them I can find continuum many that have the amalgamation property. So this is in stark contrast to the Maximova situation, right? Where although there are uncountably many superintuitionistic logics there are uncountably many superintuitionistic logics, there are only finitely many that have amalgamation. What this means is that if I look at the full lambic calculus with exchange or its false and free fragment, there are continuum many axiomatic extensions of deductive interpolation. So how does the construction go? Proof of this should give me some examples of some logics, right? I want to say something maybe. Yeah, maybe I'll just go on to. Oop. So how do I get these examples? So it involves some kind of application of some fairly refined group theory. The idea is that to define each of these continuum many logics, I have to define some quasi-variety of abelian groups. I have some quasi-variety of abelian groups that are defined in some technical way. And I think about these things as being discretely. I get one of these for each prime number, in fact. What I do is I define a residuated lattice structure by putting a bottom element on this discrete ordered thing and a top element. And I define the multiplication and extend implication in such a way where, because of the special way that this quasi-variety is defined, because groups have a lot of injective objects, I'm able to show that the variety generated by each algebra like this has the amalgamation property because that variety will have enough injective objects. That's roughly speaking the way the proof goes. They're all distinct because it's encoded in the definition of these quasi-varieties. I could give you the quasi-equations, but perhaps they're not particularly informative. Now, one nice thing about this construction is that it was designed so that I could add things to the language. In particular, I can extend this to the involutive variety. I have the same result for involutive commutative situated lattices because I can define an involution on these algebras. And I can extend it to the algebraic semantics of full linear logic because I can add the linear modalities, linear exponents, bang and why not. Algebraic linear logic is not well known, but this is a tidy application. I can put these modalities on here and I can add all of this stuff and get algebras that give me logics corresponding to the deductive system of linear logic. Actually, all of this has some modified version of the Craig interpolation theorem for all of these extensions. There's this modified version where you put bang in front of everything, linear logic case. Now, on the other hand, you might ask about, what about the situation without exchange? With exchange, we've seen that deductive interpolation is quite common. And it seemed for quite a long time that I guess without exchange, it's relatively common. Actually, if you know where to look, deductive interpolation is still quite common among logics without exchange. In particular, there are continuum many. You can take continuum many of these, viewing them algebraically. There are continuum many idempotent semilinear varieties. So these are quite special. These all have the amalgamation property and contain non-commutative groups. What this says on the logical side is that if I look RLCM, this is false and free full lambda calculus with the contraction and mingle rules. And I look at the extension by the semilinearity axiom. The semilinearity axiom, you might think of something like this. This is not correct in the non-commutative case, but it's something like the Gödel-Dummett axiom. If I look even in this restricted context, there are already continuum many that don't have exchange. On the other hand, in the same context, this is why I say exchange has a critical role. In this same context, if I restore commutativity to the picture, I restore exchange, I retain the semilinearity, I retain the idempotence, but I put exchange back into the picture, then it drops from continuum many, the deductive interpolation property, to exactly 60. And I can tell you the exact 60 of them. Now you might ask, I've told you that I'm working in the false and free fragment, right? So I don't have this point F. What happens if I do have the point F? Well, everything still works correctly, but the extra constant allows me to define many more varieties. I have not worked out exactly how many varieties there are if I add the falsum. There are at least 12.5 million or something like that. I've identified this many. You could use the methods to give the exact number. I don't think it's too many more. Maybe it's 19 million or something like that. But it's still finitely many in contrast to the continuum many before you add exchange back. So there's this kind of bifurcation, and contrary to kind of our earlier thinking that exchange blocks the deductive interpolation property, in some circumstances, the lack of exchange is really necessary in order to give us deductive interpolation. Now the proof here uses totally different methods from all of this abelian group stuff that I use for linear logic. Here you have to get deep into the dynamics of bi-infinite words to find these varieties and prove that there are continuum many. And I'll spare you the constructions, but I mean, you see perhaps some of this feeling of GALAI and Maximova that we have to get into different methods very often, but it still has some kind of structure. Now, some recent stuff that I'm quite proud of. This dates back to really Franco Montagna's work. I think Franco started working on this sometime in the early 2000s. So Peter Hayek, who in the old days was at the Institute of Computer Science, where I am now, he worked quite a lot on the mathematical foundations of fuzzy logic. And he wrote quite a beautiful book, which many of you possibly seen, where he lays out his basic fuzzy logic, BL. Basic logic is a bad name. Perhaps we should rename it to be Hayek's logic or something like that. The name is stuck if we think about basic logic. What is basic logic? So basic logic is essentially the logic of continuous triangular norms. So if you think about the compact unit interval, real numbers, and I think about a commutative binary operation that's also associative as unit 1, and I stipulate that that operation is continuous with respect to the usual topology, that's what a continuous triangular norm is. And Hayek was able to axiomatize precisely what's going on if I think about this operation as being a conjunction for some logic. So basic logic is the logic of these kinds of things. Now, there are other algebraic models of basic logic besides the ones on the unit interval. There's some kind of residuated lattices. In particular, they're called basic logic algebras or BL algebras. These are commutative integral pointed residuated lattices that satisfy these two equations. The first of them is something called divisibility very often, and the second is this kind of semi-linearity condition that I pointed out to. In particular, the satisfaction of the second equation tells me that this class of algebras is generated by totally ordered algebras. The finitely subdirectly irreducible BL algebras are all totally. This is a bit of an auspicious point for us. Now, the study of amalgamation in BL algebras, same as deductive interpolation, basic logic, has a long history. As I said, Franco probably started thinking about this, I think about 2003, as far as I can place it. In 2006, he had quite a lovely paper where he proved AP for a lot of different varieties of BL algebras that are very natural, including the whole variety of all BL algebras. And he gives uncountably many subvarieties that don't have the amalgamation property. He also shows that of these, this is talking about things corresponding to deductive interpolation. He proves that the ones that have Craig interpolation are just the super intuitionistic extensions. There are only like 2 of them that have Craig interpolation, namely the ones that are hiding algebras. Now, there have been a lot of efforts in the intervening 20 years to try to classify varieties of basic logic algebras that have the amalgamation property. One thing that I'd mention is there have been recently some very nice ceramics papers from Stefano Agazzoli and Matteo Bianchi, where they kind of creep up on this quite technical work, finding more and more varieties that have the amalgamation property, but they can't find all of them. And until recently, the main open question in this area has been to obtain a complete classification, because it feels as if you should be able to. Among other things, BL algebras have an extremely transparent structure theory that goes back more than 20 years in terms of so-called ordinal sums. We know a lot about their decidability properties, their complexity properties. We know almost everything about BL algebras. And this has been a very stubborn open question.
Going back to Hayek and his assumption concerning the segment of real numbers. What's the probability of real numbers he applies in his proof?
I don't know. I mean, I think that he freely uses all of the analytic properties of the compact unit interval. I think that he takes no non-standard approach to the reals or anything like that. He approaches it very much the way you might basic analysis. But I'm doing reverse mathematics to see what exactly is needed to get this kind of axiomization. Probably requires quite a lot of detail, quite a lot of technical work. So what I'm getting at is that we now have a classification of arbitrary varieties of BL algebras that have property. This is because of this essential amalgamation property. This is the key missing ingredient, and the fact that you can have totally ordered things in this way. So the result is actually rather difficult to state. I think it's more difficult to state correctly than it is to prove once you understand what's going on. The way I would state it is that suppose I take BH, AP to be the poset of varieties of basic hoops. Basic hoops are BL algebras, but I forget that they have a bottom node. BL algebras are usually defined as 0. Suppose I get rid of that and take 0 free set of x. And suppose I look at the post set of all of the varieties of these with the amalgamation property. In that post set, we can tangibly partition this post set into countably many intervals, countably many finite intervals, which can be explicitly described. And from this description, for basic hoops, we can then add a bottom element back on. We can add 0 back and get a very similar description for BL algebras in a completely tangible way where you can describe all of this. And therefore, a similar result holds for BL algebras. And in particular, we know the cardinality. This is a question of Franco-Montagna, is how many are there? We know that there are infinitely many, or there are uncountably many that have the amalgamation property. The answer is no, there are countably many because there's only a countable union of finite intervals. Same holds for the negation through fragment BL. This is an example of what the intervals look like. This is not comprehensible because of the way things are named. As I said, the difficult part of this is actually naming the logics or naming the varieties that have the amalgamation property. This is a smart idea of Simon Sanchi. The way these things are named is actually by some finite atomic. These are named by some kind of regular expressions, where the Kleene star here denotes the fact that I perform this ordinal sum operation some finite number of times. Concatenation just says that I have an ordinal sum between these things. But these are the kind of intervals that show up, these and some similar things. There are some finite classes of things like this, and you see the parameter n. N ranges over all of the positive integers. And so for each n, you have some finite number of intervals of this kind. Union of all of these is exactly the post set of varieties that have the amalgamation property.
Is there relations between the ones with an n and the ones with a different n?
Yes, but the relations are precisely the relations that are described by Lukasiewicz logic, because there's some kind of divisibility conditions about containment of varieties for Lukasiewicz logic. And in particular, BL algebras, the ordinal sums, Weisberg groups. And so this is where you get the relationship between the ends and how the post set fits together. It's impossible to write down the entire post set, but we completely tangibly understand this.
Model it in 3D.
You could model it in 3D. I'm not good enough at tech to put this in paper, but
I was trying to understand what it is in 3 dimensions.
this is something
It's
like
not
a
easy.
section.
It's not easy.
This is something like a section of this post set. A few more scattered examples. I've shown you some kind of successes of the techniques, I think. There are many other successes that kind of come from heuristic examples. In particular, to show failure of different kinds of interpolation, you can often run computer searches for some small counterexamples. If you were at the talk of Valeria maybe 3 weeks ago, there's something like this, right? Resolve a question for MTL algebras, some kind of generalization of BL algebras with a small finite example. There's nothing special about this example. You can similarly catalog failures for lots of small finite residual classes. Integrality, what they have, for example, this is just one knotted rule. A knotted rule is a rule of the form xn smaller than or equal to x to the n, where n is not equal to 0. So if you take such an axiom and add it to semilinear residuated lattices for any n and m, it will always fail to have the amalgamation property. And you can just get small finite counterexamples that show this. If you're probably good at programming computers or something, you can probably catalog these up to some size. One that you might get for this one, it also works to show things for semilinear varieties of relevance logics. So maybe if you look at this algebra, maybe I'll put an A here, F here. I'll put the monoid identity here, called E in this case. There are two things I could do. I could, on the one hand, declare A to be an idempotent element. It's one thing I could do. So this is one algebra in the span. An alternative thing I could do is I could declare this element to be A squared. And if I do this, I get two algebras. They contain a common subalgebra, namely this stuff. That common subalgebra together with these two algebras defines a span. And you find you can amalgamate it among any totally ordered algebras. And it satisfies some nice knotted rules. So you get the failure of a lot of these things. You get the failure of amalgamation for distributive situated lattices, for example. So you can get very, very tidy classifications for all of these. Now, to sum up the kind of positive results, so we now have a very thorough picture of deductive interpolation property for most of the logics defined by the basic structural rules. We have essentially complete understanding of the amalgamation property for all the prominent varieties of semi-linear residuated lattices. I think there are very few open questions left in that area, mostly related to lattice ordered groups and things that people have worried about for a long time, which we have no idea how to tackle. The toolkit allows us to solve a lot of long-standing open problems, stuff related to exchange, stuff related to the Hayek basic fuzzy logic, stuff like this. It's not yet automatic. I can't give you some automated tool where you just put your logic into some computer and it tells you yes or no. But it's getting very close to this because we have an arsenal of things we can try, and most of the problems become easy if we apply this arsenal intelligently. And in particular, these kinds of heuristic tools for finding small counterexamples is very powerful. And we can get a very deep catalog from this. So in just the last couple of minutes, I would like to pose a couple of open questions, which are still things that I would like to know about this. There are still some basic questions about basic structural rules. In particular, I've shown you a lot of stuff about idempotent residuated lattices that corresponds to things with contraction and mingle. I've shown you this mostly in the context of varieties that are semi-linear. One open question is how many axiomatic extensions of the full lambic calculus with exchange, contraction, and mingle there are? No semi-linearity that have the deductive interpolation property or the Craig interpolation property. When we drop semi-linearity, I don't have cardinality. There are 60 with semi-linearity without. Another open question is, are there continuum mini logics with weakening that have the deductive interpolation property? Weakening on an algebraic level corresponds to the top element being monaded. If we add exchange, same question. We don't really have the techniques to answer this yet. Some computational questions. If I take a congruence distributive variety, and the class of finitely subdirectly irreducibles of that variety is closed under subalgebras, and if I assume the variety is just finitely presented rather than finitely generated, can I then decide whether it has the congruence extension property or the amalgamation property? Actually, finitely presented is what I'm much more interested in than just a finitely generated variety, because this has a deep connection to uniform interpolation, which I can't go into here. I should mention, by the way, that this property of congruence distributive, I can't test this. It's undecidable whether a variety is congruence distributive, a finitely generated one. So I must assume it in the background. So there are many similar kind of computational questions that are still open that I would like to answer. We still need new transfer theorems. The transfer theorems have been key in expanding this theory in many different directions. One question is, can we develop a good transfer theorem for understanding Craig interpolation? So I've talked a lot about deductive interpolation. For deductive interpolation, I have good tools for reducing things to tractable generating models. Can I do this for Craig interpolation? It seems that it's much harder because Craig interpolation it's essentially not a categorical property, right? It depends really on having an ordered algebra, very specific to the language. Another question is, can we obtain convenient transfer theorems for quasi-varieties? I've given you some transfer theorems for quasi-varieties, but they depend crucially on me understanding what the class of relatively finitely subdirectly irreducible members of a quasi-variety are. For a variety, I know what the finitely subdirectly irreducible members are. It's very tractable to get those very often, but the relatively finitely subdirectly irreducible members are rather inscrutable. So it would be nice to do this for some things that have actually worked for quasi-varieties in the past, like critical algebras and things of this nature. And I'd like to just end with perhaps the biggest problem in this theory. Sometimes people in amalgamation call this Janssen's problem. And I've phrased it here kind of for substructural logics. But Janssen's problem posed by Bernie Janssen more or less asks the following. Are there techniques for determining whether a class of mathematical structures has the amalgamation property based solely on the shape of the axioms that define the class? In other words, could I look at axioms like this, perhaps with some other axioms for the variety, and simply decide based on the form of these axioms that yes, we have an amalgamation property. Something like a Maltsev theory for amalgamation. So the very ambitious question, in general, the answer is we have no idea. And we have no idea even for special cases like residuated lattices or even special classes of residuated lattices. But it feels like we're inching closer to being able to answer big questions like this. And I think we've made a tremendous amount of progress on this. There's more to come. So I think with that, I'm 5 minutes over. So I'll thank you for
Questions, comments? So one of the questions was about commutative identified lattices. In involutive case, there's a good structure theory, but I don't think we tried to look at this problem. No, the answer.
I have no idea in the case.
For Sugihara algebras, do they have amalgamation?
Yes, there are exactly 3 varieties, subvarieties of Sugihara algebras with amalgamation.
This is much bigger, and so this should be one of the things we should check.
Yeah, so it's possible your structure theorem is a key to opening that up.
Or just the techniques you have. I don't really work. Just so very nice.
In the very last slide, you mentioned Johnson problem. Do you know if he took inspiration from Alquist's theorem for modal logics?
This is the impression I get talking to Berka and people like this who knew his process.
So I have a little role. Another funny remark, it's not a question. If you go to slide 12, no, so I did not, where you make a summary of the situation. Yes, so, with all people, beginning with Craig and so on.
Oh.
It is just a curiosity.
Here we are.
Oh, 20. I do not see well. So I know 90% of those people. I met personally, including Craig, Maximova, Hitz, Gilardi, Ajek, Dinola, Lettieri, Montagna, not the younger ones, but
Only the old guys.
Craig was a very nice person.
We'll have to talk about Craig. I'm sorry I never had the opportunity to meet him.
He was already pretty old when I met him.
Went hiking with him in the Rocky Mountains. I went hiking with him in the Rocky Mountains.
Really?
And then we lost him. He decided to go down earlier. He didn't want to go quite as far. And when we got back, he came back. It's very nice.
He was a very nice person.
Yeah.
So the papers that you had there for class, this means that they are not published yet.
Yeah, these are papers that the referee will take a long time to read, I guess. I've recently had papers that the referee has kept for like 3 years, so hopefully the referees will be a little quicker on some of these. They're on archive, so you can.
So why Why is it exactly 60?
I mean, this essentially comes down to the structure theorem for commutative idempotent residuated chains. And if you consider V formations of some such things, this is a locally finite variety. So I can consider V formations of spans of finite ones, in fact. And if I worry about this, it turns out that briefly the structure theory says that I have some kind of skeleton, which is like a Sugihara monoid. It's some kind of intuitive structure. And then off of this skeleton, there are sometimes points hanging off the main skeleton. And it turns out that if your variety has amalgamation, then you either have 0 points or exactly 1 point hanging off, or you have infinitely many points hanging off. I can't have a block like this, skeletal block where I have exactly 6 or something like that. So if you consider the combinatorics of the situation I've just described and you work it out carefully, it comes out to exactly 60.
Other questions or comments? Thanks. Question again?
Thank you.